Okay, thank you. And so I think you're hearing me through the microphone. Is that okay? Yes? No problem? Well, it's very nice to be back in Vienna. I've been there last time. It was quite, maybe 10 years ago. And it's always nice to come here. And so I would like to thank the organizers for the invitation. And I gather this is a mixed audience. There are people from combinatorics, people from free probability. So I will give 3 lectures. The first 2 lectures will be devoted to free probability, and it will be an introduction for people who are not familiar with this topic, and probably there are some in the audience. And the last one will be purely combinatorics. It will be on another topic, of course related to non-crossing partition, because it is the topic of the conference. So let us start with free probability. So I will start with the basic facts about non-crossing partition that everybody, I think, here should know, but just to make sure that you are familiar with that, I will make a quick introduction to non-crossing partition and the symmetric group. So we start with Cayley graph. So if you have a group and a set of generators, you can construct the Cayley graph by putting an edge between 2 elements which are related by a generator. And in the symmetric groups, generally there are at least 2 sets of generators for which this is an interesting object to look at. The first one, which will be interesting for us in non-crossing partition, is a set of all transpositions. The second one is a set of elementary transpositions, which really is a set of Coxeter generators. And actually, this second set gives rise to the weak order that will appear in my talk, in my last talk, the third talk, but not the first 2 ones. Okay, so since the transpositions are stable on the conjugation, the left and the right Cayley graph, they coincide. And the fundamental observation is that if you have a cycle, and you multiply by transposition, in which the 2 elements of the transposition are in the cycle, then you break up the cycle into 2 parts. Okay, so that's also a very elementary thing. And using this observation, we can compute the length function associated with the Cayley graph. So if you have a graph, you have a length function of the graph defined naturally. And so the length function of a partition is the number of elements in the generating set that smallest number that you need. In this case, it's n minus the number of cycles of the permutation. So the distance in the Cayley graph is the length of sigma 1 times sigma 2 inverse. So here, for example, is a Cayley graph of S3. I put the identity below, and you see that there is a gradation according to the length of this graph. Here is the same, not the same, but the Cayley graph of the S4, the same idea, but slightly more complicated. And again, you see there is a grading, naturally, when you're oriented from the identity. And this gives rise to the absolute order. So the absolute order states that there is a covering relation between 2 permutations if they differ by transposition, and the length of one of them is equal to the length of the other plus 1. And they are ordered in this way. And so in this order, we have a permutation pi is smaller than sigma. If, I should correct this. That's the opposite, which is true, that pi is on a geodesic path from the identity to sigma, in this case. But E is the smallest element. Yes, I think there is, I have made an intervention between pi and sigma somewhere, because, okay, no, if you read this line, yes, it's okay, but I think, but I show you here, so this is the graph for the absolute order. And in it, the maximal elements are the elements which are the farthest from the origin, which are the elements which have only 1 cycle, because the distance is n minus the number of cycles. And well, of course, the most interesting object for this conference is the interval between the identity and the full cycle, 1, 2, 3, 4. And it is exactly the set of non-crossing partition. If we have an element sigma in this interval, then if I represent the cycles of sigma, they form a non-crossing partition of the points of the circle, and each cycle it traverses in the same order as the cycle. So, of course, you know that this is a lattice for the inverse refinement order, this set of non-crossing partitions, and they are counted by Catalan numbers. And sometimes it's useful to use this linear representation of non-crossing partitions. You forget that you are on a cycle. You just keep the natural order on the integers. So here is a K-graph of non-crossing partition of order 3 inside, well, it is absolute order, the interval for the absolute order between in and 1 to 3 inside the K-graph of S3. It's in red on the picture. And you have the same for the picture of size 3. So I guess everybody more or less knows this, and certainly if you are in this conference, you should be familiar with all these things, okay? So here is a picture of the lattice of NC04. And last thing that I will need is a Creveras complement. So you start from on the left with a non-crossing partition, pi. You put red numbers between the blue numbers, and you join them with a non-crossing partition so that you have the largest possible cycles in this non-crossing partition. It's given by a very simple formula. K of pi is pi minus 1 times C. C is the full cycle. And this Creveras complement plays an important role in all this theory. It's an anti-automorphism for the lattice structure. And actually, the group of all automorphism and anti-automorphism is a dihedral group of order 4n that you see it acts on the picture on the right. If it preserves the colors, it's a dihedral group of order 2n. It's a set of automorphism, and if it exchanges the colors, then it is a group of anti-automorphism. It belongs to the anti-automorphism. Well, that's it. And now we start with, I think everybody is familiar with what I just said. So now let's see things for which some people on the audience may be less familiar with. Free probability and random matrices. So I will have a little prologue about a very simple model in probability theory. You take Rn, a big N, and a small n, where you take small n vectors. And small n will be fixed. You fix the norms, and you take the VI's vectors, which are independent vectors, taken at random with a uniform distribution, on the set of vectors which have a radius, which have a norm equal to AI. Okay? Well, when n goes to infinity, so you fix small n, and you look at this model. So when big N goes to infinity, then with high probability, these vectors will turn out to be orthogonal, or at least up to a small error. That is, the probability that this inner product will is smaller, is bigger than epsilon, will go to 0 as n goes to infinity. You can. What? No, it doesn't matter. You could rescale everything. Okay. As long as as long as the lengths are fixed, it doesn't matter, of course. No, but it's because in the next for the matrices, it will be important to have different spectra. So in this case, I have only one parameter to play with. But, then no, of course, this is not true. Of course, not true. It's not true for if you let n go to infinity, like big N, of course. No, if it goes slowly enough, yes. I mean, you can do the computation. Actually, it's not very. You can compute this. It's almost explicit formula. I mean, so it's very easy to check. But of course, it depends on big N and small n. So I mean, not this probability, but if you have many of them, you have to add the probabilities so to get an upper bound. So you have to be careful. But here I just fix small n. So when n is large, what this says is that the geometry of independent vectors becomes frozen. With high probability, if you look at the matrix of the inner product, it becomes diagonal, essentially, up to a small error and with very high probability. So now we will look at the same kind of problem with random matrices. So instead of looking at vectors up to a rotation, we will look at matrices but considered up to unitary conjugation. So let me start with a very simple example. You take two n by n matrices, which are orthogonal projections on surfaces of dimension n over 2. So these matrices will be of the form like that. So we have the identity here, 0, 0, 0, and we rotate by some, we conjugate by some unitary matrix, which is chosen at random, independently for pi 1 and pi 2, and taken with a R measure on the unitary group. And now you compute the spectrum of pi 1 plus pi 2, and you will get, with very high probability, we'll get, I did that for n equal to 800. I did the experiment. You get some picture like that, and you will already get something which looks like this shape. And in this shape, there is a curve here, which is the density of probability, which is represented here. So of course you have to rescale it to, if you want to have it to fit with the histogram, so that the integral is equal to 1. But essentially, you will get always the same picture. So that this means that the set of eigenvalues, they will always be distributed like, with something which looks like that, and it goes to infinity. So really something is going on with the matrices in this high dimensional limit. But of course, the geometry of matrices is much more complicated than the geometry of vectors. We need much more numbers to encode these geometries than just the inner products. Okay? So for one matrix, what we need for if you have one self-adjoint matrix L and another one M, then they have the same spectrum if and only if there is a unitary which conjugates one to the other. Instead of using the spectrum to describe this conjugacy class, it is very convenient to use these numbers, the traces of the powers of the matrices, which are, gives you if you want, the power sums of the eigenvalues. Because these are polynomial functions on the same matrices, much easier to deal with than the spectrum, for which you have to solve a polynomial equation. Okay, so if two matrices have the same moments, I call these the moments, and they will have the same spectrum, and they will be conjugated by some unitary. So a bit of notation. When I write a trace with a small t, it's the big trace divided by n, so that the small trace of the identity is 1, not n. Okay, and now what happens if we have a set of self-adjoint matrices, M1, M2, and n? Then a basic theorem of invariant theory tells you that the non-commutative moments, that is all these numbers, and the traces of all monomials into the matrices, they form a complete set of invariants of the matrices up to conjugation. That is, if two sets of matrices share these numbers, then there is, this is exactly what it's meant here. If two sets of matrices L and M satisfy this equation for all the choices of I1, I2, IR, and then there exists a unitary matrix which conjugates them for all I. And this unitary matrix doesn't depend on I. It's the same for all the I's, of course. So this is the analog for many matrices of what we have seen for when you have just one matrix, when you characterize the spectrum by just the moments. But in general, of course, you don't need, if the n here is fixed, you don't need all these numbers. You just need finite bunch of them, large enough. But since we are going to let n go to infinity, so it doesn't really, I will not bother to try to understand how many of these numbers I need. So now let us look at a random matrix model. This random matrix model is the following. So I take my matrix Xi to be the conjugation of a diagonal matrix Di by some unitary. So Di is a diagonal matrix of size n. Ui is a random matrix taken with a Haar measure, and all the UR are independent. So this means that we fix the spectra of the Xi because we choose the Di, but then we choose the eigenvectors at random and independently of each other. And well, a theorem, a basic theorem of Weyl-Kulescu states that as n goes to infinity, all these mixed moments, which are here, that is the traces of powers of xi1, xik, they are given as by explicit polynomials in the moments of the individual matrices. And by this I mean that they are given by some polynomials. That means that there will be a small error, and with very high probabilities, the error will be very small. So this is, I don't give epsilon delta statements here, but I mean, this is the analog of what we saw for the set of vectors. Okay, so here is an example. If you take the trace of x1, x2, then it will be, with very good approximation, it will be the product of the traces of x1 and x2. And the same will be true if you take the trace of x1 to the k, x2 to the l. It will factorize. But if you take more complicated monomials like this one, x1, x2, x1, x2, then you will have a polynomial here in the traces of x1 and the traces of powers of x1 and traces of powers of x2. But it will not factorize in the sense, the simple sense that we have here. So here, when I put this tilde here, this means that the difference between these quantities will be small with very high probability. So that means that if you know the spectra of the x1 and x2, then you can predict all these numbers with high probability, small error. Okay, so in particular, if we know the spectra of x1, xn, in this matrix model that I mentioned, then we can compute with a good approximation the spectra of any polynomial in the Xi. For example, if you want to look at the sum, the spectrum of the sum is determined by the power sums of the eigenvalues of x1 plus x2, so these moments here. You can explain these moments into monomials in x1 and x2. And if you know how to expand this into polynomials into trace of x1 to the k and trace of x1 to the k, then in principle you can recover these numbers with good approximation, with high probability. Excuse me? Yes. Oh, no, I mean, all these numbers for all case. Yeah, yes, exactly. Like, you see, I have this here. I have trace of x1 and trace of x2 to the square. Of course, you can have mix. I mean, it's a polynomial in all these quantities. Okay, so the Weyl-Kulescu theorem, it follows from his theory of free probability, which is a non-commutative version of classical probability, and in which the independence of random variables is replaced by a new notion, that of freeness. And this is what I'm going to explain, and then we will see that freeness is deeply related to non-crossing partitions. Because the discoveries that Roland Speicher made years ago. So what is the context? The context will be a complex algebra, A, with a unit element, 1, and the linear form from A to the complex numbers. That tau of 1 is equal to 1. So yes? Oh yes, C is a complex number. Yes, yes, it's, everything is about above the complex numbers. Yes, it's an algebra, like a matrix algebra, if you want. No, of course, it will not be commutative, definitely not, but it's an associative algebra, like typically the algebra of n by n matrices, for example. No, in general, it will be infinite dimensional. For interesting examples, it will be infinite dimensional. So we have, yes? Tau of 1 is equal to 1. It's a normalization condition. Yes, and 1 is the identity. T is a complex number. 1 is a complex number. What? Oh, yeah, no, okay. That's, I don't know. Yes. It should be 2 points, if you prefer. Okay. Yes, just means that tau is a map from A to a complex number, a linear map. It's like the expectation in classical probability theory. It plays exactly the same role. So the definition, which is due to Voiculescu more than 40 years ago, suppose you have subalgebras in this big algebra A with this linear map tau. They are called free in the following order. Suppose you have elements A1, AN in the big algebra, and such that all these have a zero trace. I will call tau the trace if you want, if you don't follow me. It's the expectation in some sense in probability theory. And each of these elements belong to one of the algebras, A1, A2, etc. And I ask that no two of the algebras, neighboring indices here, are equal. Because if I had two neighboring indices, I could take the product and it would remain the same algebra. So I want to avoid this situation. So if these two conditions are true, then you have tau of A1 is equal to 0. So this is a bit strange definition. That's the first, maybe if it is the first time you see it. So what I should stress is that this definition, freeness, it's a way of putting together probabilistic independence and algebraic independence. It's not obvious from when you see the definition, but it is actually what happens. Well, a priori, you have no connection between this definition and random matrices, but on the other hand, if you think of independent matrices of very large size, then, well, if you take them independent random matrices, they certainly have probabilistic independence. And if your size is large enough, your matrices will satisfy very few algebraic relations. In general, for generic matrices, a set of algebraic relations that they satisfy, at least for, they will not satisfy any small degree algebraic relation with generic is probability 1. So this is realized by random matrices in some sense. So at this stage, this is only words, but it's just to help you understand the context. Algebraic independence? There is no, it's not. Well, it is hidden there. It is hidden. It's not apparent. It is behind. Yes, you see a kind of probabilistic independence, but it is this second condition here which contains the algebraic independence in a hidden way, if you want. It's not obvious. So the point of this definition is that you can do computations. How do you compute? Well, I give you an example. If you have an element A1 and an element A2, which are in two free algebras, what you do is you take A1 and you write it as its centered version, A1 bar, and you add the expectation, tau of A1 times the identity. Do the same for A2. Now you want to compute tau of A1, A2. So for this, what you do is you write each of A1 and A2 as above, like that, and you expand. And you have 4 terms. Now it's very easy, using the freeness assumption, to see that the result is 0. it means that you like physicists do, you take expectation. Or you remove, sorry, you remove the expectation to center the variable. O of A1 is the expectation.
Shift.
Yeah, it's a shift by so that you get something which is centered. There is a unique way to do that by translation. This is what I do. So now using freeness, you have this, and now if you expand this, you see that finally you have this factorization. So this is a very simple computation. Well, you can do the same if you have 4 terms like that, A1, A2, A1, A2, where you can write A1 and A2 like that, the centered version plus a constant. You expand, you use this, and then you make some more computation. And then you find this formula, which is here. Remember, this is a formula that I showed you before when I was talking about random matrices. And well, in general, what you expect, as you can prove actually, is that tau of A1, AN will be expressed as a polynomial. So A1, AN are elements. Each of them is the sum algebra, and the algebras are free. And it will be expressed as a polynomial of tau of, in the variables, tau of AJ1, AJK, where AJ1, AJR are all in the same algebra. So if you, in order to compute this, you need only to know the restriction of tau to each of the algebras. You don't have mixed terms in these products here. So if the AI are free, then the restriction of tau to each of the AI determines the tau restricted to the algebra generated by all the AI. What it means. So it's a condition. It's a bit like in classical probability. If you have independent random variables, you know the distribution of each variable, then you know the joint, and you know they are independent, then you know the joint distribution of the variables. So this is exactly the same thing, and this occurs and you can prove this using this kind of computation. What? No, you cannot see it because you have to go through the computation. There is a 16 terms, and then you have to do reductions, and you have to do some induction on the length of the formula. So you cannot see it like that. It's not easy to see it. So I mean, try to do it's a good exercise. If you are not convinced, try to do the computation for yourself, and you will see it, how it appears. But it's not obvious. I mean, I cannot do that on the whiteboard because it's a bit messy. No, but I mean, you have to compute tau of A1 bar. You have to compute all these things. So it's not clear that you will have. I mean, here you have A1 squared, and the N1 squared you have to center it also. So that's why you get all these things. What? Tau of AI bar is equal to 0 by definition of AI bar. It is a shift of AI bar, so to make it centered, to have expectation 0. Yes, but of course, yes, but on the right you have, for example, you have tau of A1 bar and tau of A1 bar squared, which will appear. Yes, okay. But you really have to go into the computation. I mean, if you don't go into the computation, you don't see why it appears. It's not obvious. I mean, you have to reduce this because here I have no bar anymore. Okay, that's the reason. Okay, so now let me go back to my model of matrices that I mentioned before. So I take diagonal matrices, I conjugate them by random unitary matrices. Now the spectra of xi is fixed, the eigenvectors are chosen at random. And the theorem of Voiculescu is that as n goes to infinity, the x are asymptotically free. That is, it satisfies the vanishing condition of freeness up to a small error and with probability close to 1. This is well, of course, the statement of the theorem should be a bit more technical with epsilon and deltas, but I will spare you that. Just say in words what it means. In particular, the mixed moments, which are here, are given by explicit polynomials in these moments with high probability and with small error. And these are exactly the polynomials that I mentioned before. Okay. So, of course, the explicit computation of these polynomials is a difficult task. I mean, as you can see, the answer, it's not very non-obvious what will be the answer. From the algorithm I gave you, it's really messy to do the computations. So you need some tools to do that. And that's where non-crossing partition enters the game. And so this computation, this can be done using the theory of free cumulants, which is due to Roland-Speicher. And this really allows you to make lot of computations that would be really messy with method diagrams. So it really changes the game as far as computation are concerned. So let me explain that. So I don't know how much time is. So it's 10:15. Okay, minutes, that should be enough. So let me explain the connection between freeness and the free cumulants. And the free cumulants is where the non-crossing partition will appear. So again, we take the same context. We have a complex algebra, an element 1 in A, and a linear form. Sorry, there is still this equal, which bothers Christian. I should change, when I give you the slides, I will change the tau so that I don't get an email from Christian. So tau is a map from A to C, and tau of 1 is equal to 1. So what are the free, or sometimes they are called free cumulants, sometimes non-crossing cumulants. I don't know, Roland, what do you prefer? You prefer free cumulants? Okay, let's call them free cumulants. There are n linear forms which are defined on the algebra A. By n linear, I mean multilinear form with n entries. Okay, so Rn. So they are given by this implicit formula. If you have some elements, A1, A2, An, in this algebra A, so for the moment, there is only one algebra. There are no free subalgebra, nothing. Just one algebra. Everything will be completely, it will be an algebraic theory about what you get when you have an algebra and a linear form on this algebra. Okay? And so now what you do is you express this as the sum of a non-crossing partition of R pi of A1, A2, An. So here, what does this mean, R pi? So R is indexed by the partition pi. Pi will be a non-crossing partition. And evaluated on A1, A2, An, it will be a product of R of AI1, AI pi, where I1, I2, I pi is a part of the partition in this order. And here, this is the size of the part of the partition. Okay? And this is a, yes? Block of the partition, yes. Okay. It's a partition into blocks, not into parts. Okay. So it's not a blockation. Okay. So let me give you examples just to see what this means. So the first example is when I have only one non-crossing partition, which is partition of 1. So tau of A1 is just R1 of A1. So the first linear form, R1, is equal to tau. The second linear form, it is given implicitly by this formula. Tau of A1, A2 is R2 of A1, A2, corresponding to this non-crossing partition, plus the product of the parts, the blocks, sorry, of this partition, 1 union 2, R1. So we get these two relations. So the first is tau, and the second is tau of A1, A2 minus tau of A1, tau of A2. And you see this is something which is in classical probability, this kind of, so this is the expectation, and this is known as the covariance in general. in the context of classical probability. It's kind of view the covariance. A slightly more complicated example. When we have 3 non-crossing partitions, of course, you know there are 5 of them. And so you have the first term, R3, and then you have corresponding to the partition with 1 block. Then you have 3 partitions with 2 blocks, which are here, which give you 3 terms. And you have 1 partition with 1 block, which gives you. And now you have to invert this expression. But here you don't know what is R3 yet, but you know what is R1 and R2. I gave you the formula just before. So by induction, you replace R1 and R2 by their expression into tau, and in the end you get this formula. Okay, and you see there are minus signs again. Yes? Yes, well actually, in this case, all are, for n equals 3, all are non-crossing partitions. All partitions are non-crossing. So the first difference between this and the classical case is for n equals 4. Okay. But here, essentially the same formula holds. If you know about the theory of cumulants in classical probability, for the moment it's the same. I'm not sure, but I'm not sure who discovered this. What? Yeah, I'm not sure who introduced that. Berger, really? You think? He found the Möbius function, certainly, but I'm not sure that he defined the cumulant, because I think the cumulant probably had been known by physicists. Yes, probably. Maybe it was, okay, let's talk that later, because, but the point is that in classical probability, cumulants play a role, but much less important, because we have lots of tools in classical probability to deal with independent random variables, and many of these tools are not present in free probability. And in free probability, the free cumulants play a much more important role, because basically this is the only tool, or one of the only tools that we have in this context, which is highly non-commutative. So there is an inversion formula. As I told you, you can get it by induction, but actually it is given by the Möbius function on the lattice of non-crossing partition, an explicit formula in terms of tau here. So in order to explain this, of course, you know that every interval in the lattice of non-crossing partition is canonically isomorphic to a product lattice of non-crossing partitions. And the number of terms is the number of blocks of pi2. And the Möbius function is given on the product of the blocks, of the lattices. It is given by Catalan numbers with a sign, product of Catalan numbers with a sign. And now we come to the fundamental theorem, which relates freeness and the vanishing of free cumulants. So it is a theorem that Roland proved about 30 years ago. Suppose the AI are free in A. So we have, again, same context, complex algebra A, a near form tau, and a family of subalgebras is free if and only if the mixed cumulants vanish. What does this mean? That is, if you take any sequence of elements in the algebra, A1, A2, AN, you assume that each of them belongs to one of these subalgebras. Then the free cumulant is 0 as soon as you have 2 different indices. The algebra, the A1, AN, at least 2 different algebras occur. That is what mixed cumulants mean. Mixed cumulants means, of course, if you are just inside one of the algebras, these numbers can be anything. I mean, you can use them, lots of choices, and freeness doesn't tell you anything about what happens inside one of the algebras. It only tells you what happens when you mix the algebras together. And in this case, what it tells you is that all these mixed cumulants vanish. This is the theorem by Roland that this freeness condition, the Voiculescu definition, is equivalent to the vanishing of the mixed cumulants. And it is absolutely fundamental, and this is what allows you to make computation with. And I think we will have the sequel next time. Just on time.